So just follow along. All right, so what is sound? Sound is created by vibrations. So a vibration is the complete front and back motion of an object. So what I would do is I would write this little piece down under like, what is sound? So I would definitely write this down in my notes. It's really important. It's a complete back and forth motion of an object. So how do we get this back and forth object? Well, it is a longitudinal wave. So remember how we talked earlier about how we have transverse waves that look something like this, and then we have our longitudinal waves which look more like this, right? So this one is going to be more of that longitudinal wave, right? Which means that they can travel in all directions away from their source and not necessarily stuck going in one linear direction. Air or other matter does not travel with the sound of waves. It's literally just particles pushing against each other for going from one spot to the next spot. So as you can see kind of here, as the speaker here is vibrating, the particles are closer because obviously the sound is coming from here, and the sound waves, or the energy, as all really waves are, is energy. The energy is traveling from here and then travels here and then travels here and then just keeps on traveling out. Just like you can kind of see it happening here. That is going to continue to move outward. The energy just continues to move. All right? So, a sound wave will travel as a, you guessed it, longitudinal wave. Remember, sound waves are longitudinal. Transverse waves, fun fact. EM waves, remember? Yeah. All right. So a medium, write this down. A medium is a substance through which a wave can travel. So I would write that down, and I would definitely write that all sound waves require a medium. So unlike the electromagnetic wave, so light waves do not need a medium. They don't need a medium, but sound waves do. Sound waves need a medium. Okay? So remember that, and remember how they're going to end up interacting with each other, because one needs a medium and one doesn't need a medium. That's going to be our basic, our one of our main points between the two, between a light wave and a sound wave. So, sound waves must travel through a medium. Which of the following would sound waves not travel in? Remember, a medium is going to be a state of matter. So you're talking solids, liquids, and gases, right? So that means a vacuum is going to be our right answer here. You can scream in space and no one will hear you. Remember that. So that's a vacuum. Sound cannot move without particles around it. So now let's get to the different properties of sound. So the speed of sound, sound will travel through the air at about 343 meters per second, right? But the speed of sound is not always going to be this 343 meters per second, because sound waves travel at different speeds through different mediums. I would write down this little piece here, that sound waves can travel at different speeds in different mediums. Keep that in mind. That's a really big test question. We always want to bring up which one has to require a medium and how does that affect the wave itself. So sound waves are going to travel at a different speed depending on which medium it's traveling in. The speed of sound depends on the characteristics of the medium and the sound that travels through it. But yeah, this is our main point here. We need to make sure we have this in our notes. Okay? So the following chart summarizes the speed of sound through different substances. Now I want you to notice something. Remember how I said that sound waves are going to require a medium, right? Because sound waves are requiring a medium, we have to think about why it's needing this medium and how it's really affecting this wave, right? Because a wave is really just carrying energy from one space to the next, or moving energy from one area to another area. So if we think about a solid, right? In a solid like block of ice, all of the atoms are real close together. All the molecules are real close together, right? In a liquid, they're kind of close together, but they're also like kind of just chilling by themselves. In hot air, remember, they move a lot faster in hot air than in cold air. Not that there are less of them, they're just moving at a lot slower rate. Hot air, the more temperature, more energy. These things are like pew, pew, pew. They're like kind of going everywhere, right? And then we have the very slow cold air, right? So when we think about solids, liquids, hot air versus cold air, right? The particles are what's going to make the difference. So in a very fast area, so if I have sound that's moving very quickly, it's going to move very quickly in a solid because the particles are so close. It's going to move okay in a liquid because the particles are still kind of close to each other. They can still bump from one area to the next. In hot air, the particles are moving so fast that it's more likely that they're going to bump into each other and carry that energy from one to the next. Cold air, they're not moving quite as fast, and because it's air, the particles are spread out a little bit further apart than they would be in a liquid or a solid. So it's going to travel the slowest the colder the air is. So keep this in mind. So, for example, let's look at this chart. In what state of matter does sound travel the fastest? Notice the sound is traveling the fastest with steel, right? And it's traveling the slowest in freezing air. So notice the air is at 0 degrees Celsius. Our steel isn't that much hotter, but remember our particles are a lot closer together in steel. Remember, steel is a solid. The particles are like right on top of each other. They're really, really close. In air, they're kind of like just chilling. They're like living their best life out here, right? So when you're trying to take something from one area to the next, it takes it a little bit longer to go to the next particle as opposed to steel being right next to each other, right? So that's kind of the relationship between temperature and the speed of sound. So the temperature and the speed of sound, how do I want to do this? It's like I said earlier, you know, the hotter it is, so I'm going to say the hotter the medium, the faster it's going to be. The faster speed of sound. However, even though it moves faster through a hotter medium, at the end of the day, it's really going to come down to your solid, your liquid, and your gas. If your solid is at 0 degrees Celsius and your gas is at 100 degrees Celsius, it's still going to move faster in that solid than it is in that gas. Just because the solids, like I said earlier, are all packed really close together as opposed to the gases, which are a lot further apart. So, sound travels fastest through which of these materials? Remember, it can't travel at all through empty space. And so now we have our solid, we have our liquid, and we have our gas. And the particles are closest in a metal, in our solid. So it's going to be a solid or the metal. Without matter, sound waves could not travel. That is true. Remember, sound waves need a medium. They need it. They absolutely need it. They can't travel. This is why we put so much emphasis on particles and how far apart they are and how close they are, because sound waves absolutely need those particles. So here again, we're just reiterating the whole idea of temperature. So I would just write this little piece down right here. that sound waves are going to travel slower at lower temperatures than at higher temperatures. They're going to travel a little bit faster just because the particles, are moving a little bit faster in hot temperatures as opposed to in the colder temperatures. That's all you kind of really need to know about this one. This is just again reiterating, is just showing you kind of the relationship between temperature and speed in the form of a graph. So you notice that as it gets a little warmer, then the speed, so as temperature is increasing here, the speed of the particles are also increasing. So that's all you really need to know from that slide. Frequency and pitch. So remember, we talked about frequency and pitch before when we were talking about, just waves in general, and we kind of touched on it again in the last unit with the light waves. So remember that frequency is the period, or is the number of waves in a given period. So if this was my given period, like from here to here, and then again from here to here, we're trying to see how frequency occurs, right? So here I have, whoops, what just happened to my life? Okay, here it is. So here I have 1, 2, 3, 4. I have 4 here, and I have 1, 2 here, right? So I have 4 vibrations happening here, and I have 2 major vibrations happening here. So the higher the frequency, the higher the pitch. Just like when it was the higher the frequency, the more energy it has, same deal. The lower the frequency, the lower the pitch. Put this in your notes. Dun, 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 dun. Notes. Notes. Please. Please. Okay. That's just a little YouTube video you can watch in your spare time. Alright, so frequency and hearing. So sounds too high to hear are called ultrasonic. So ultrasonic sounds mean that the sounds are so high pitched that we can't hear them. So bats are a really good example of this. They actually use it to find food because they're blind. So they have to hear out, and they have super hearing, and they can hear ranges as far as 2,000 to 1,100. 100. Why can't I say words? I can't say words because it's the end of the day. Anyway, 110,000 hertz, as opposed to a dog that can hear a little bit better than us, but we're kind of we're not the worst. Elephants can't hear at all. Oh, poor elephants. Anyway, so yeah, sounds that are too high to hear are called ultrasonic. Notes. Okay? But Miss Miller, what's an ultrasonic wave? Okay, an ultrasonic wave is going to be a sound with a frequency above 20,000 hertz, and it can't be detected. Just like there's only amount of visible light that we can see, there's only amount of sounds that we can hear. So we just have to accept the fact there's a whole unknown world all around us that we just can't even process. Ultrasonic waves are used in sonar as well as in medical device or diagnosis and treatments. And sonar is used to estimate the size, depth, shape, or underwater objects. So typically we'll use ultrasonic waves to detect different things going on that we can't see. An infrasonic wave have frequencies below 20 hertz. So these are super low sounds. These are produced by sources such as a heavy machinery or thunder. So you get that loud thunder rumble, and it kind of makes your stomach go, oh my. Yeah, those are those infrasonic waves. So infrasonic just means it's a low wave, or it's a low frequency wave. Ultrasonic, high frequency. All right. So I would just make sure that I have this kind of connection happening. They're never going to ask you anything like this, but they will ask ultrasonic waves, are those high or low? So just need to know those. The Doppler effect. So the Doppler effect is a change, obviously write this down, is a change in sound frequency caused by the motion of the sound source or the motion of the listener, or both. Basically, all this is really saying is, how sometimes you'll hear fire trucks zooming by, and you hear it in the distance, and then all of a sudden you hear it super close to you. It's just because of the compression and rarefaction of the wave. So you know how we said that sound waves are those longitudinal waves, meaning that they travel like dun 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 dun. You know, they kind of squeeze together and then like pull apart and then squeeze together. So because they're being compressed here, this is going to be a louder sound than these back here, because the wavelength here is a lot longer than the wavelength here. So this is going to sound a little bit quieter than here. So if I'm standing, ding, there's me. If I'm standing here, it's going to sound a lot louder than it would be if I was standing here. And that can change depending on where the fire truck is, you know? Like I said, physics just explains daily life. So the Doppler effect is just explaining why sounds get so much louder when they're close to you as opposed to far away. Just like, you know, it's really annoying when you hear a mosquito, but like you only hear the mosquito when it's like right at your ear, right? You're not going to hear the mosquito when it's like flying around the room somewhere. Well, some of them you probably can, but especially when they like zoom past your ear real fast, it's craziness. That's a really good Doppler effect when flies are zooming past your ear. So annoying. Anyway, so again, Doppler effect, you're dealing with a moving source. So we have this guy here. He's going to hear the sound a lot more than this little girl over here, because these are compressed. These are a lot farther apart. So my frequency here is low. My frequency here is high. So this is going to be louder and this is going to be quieter. Just another example here. As the sound approaches you, its frequency and pitch increases. Write this in your notes. Same with this one. And as the sound source goes away, so as it approaches you, it increases. These two increase. As it's going away from you, these two decrease. And I'm going to erase this because I wrote all over that, and now you can't even write because I decided to be obnoxious and write everywhere. Okay, but yeah, these two in notes. Okay. We're not going to go with this one right now. Let's see. Which observer will hear the higher pitch sound? The higher pitch sound will go to R. Because as you can see here, it is compressed, and the lower pitch sound is going to go to L because we have a larger wavelength, which means we have a lower pitch, lower frequency. More YouTube. Loudness. What is loudness? We're always talking about things that are really loud, right? So loudness is the amount of energy a sound has, right? And a sound wave with a high amplitude, this is important. A sound wave with a high amplitude is very loud, and a sound wave with a low amplitude is very soft. So if you ever like watch those old 80s movies and they're like over there dancing, living their best life, and they're like, hey bro, turn up the amps. That's what they're talking about. And it gets louder, and then they're all like really dancing because they're happy that's loud. Yeah, so amps or amplitude is what's going to give you your, it's going to give you your loudness. So an amps that are like do 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 do. I know this is a transverse wave. Chill. Let me be great. All right. So if the waves are really low or the amplitude is really low, then it's going to be a very soft wave. But if our amplitude is up here, it's going to be a really loud wave. And you can probably like look on like YouTube and stuff and actually see different like amplitudes for different sounds. They do it all the time. Decibels. Decibels is, the loudness is measured in decibels. So decibels is just the unit for loudness, pretty much. We're not really going to test you too much on this. Just understand that loudness and decibels are related, and you should be good for that. So, loudness is represented by what part of the wave? That is going to be your amplitude. Amplitude is going to give you loudness. That tells you how loud something is. So, for example, when we're talking about decibels, decibel level 0 is the softest sound you can hear. You know, just picture someone whispering, oh, so very, very softly. And then like a rocket engine 15 meters away is like 200 decibels. So it does get pretty loud. And at some point, at this level here, that's your threshold for pain. So if you're like standing at a concert and the speakers are right next to your ear, if it gets any louder than 120, it'll actually start to hurt your ears a little bit. It's shaking your poor little eardrum to the max. And it's just too much. So again, here we're going to look at, kind of see amplitude and frequency. So this is a lower amplitude here. And this louder one, or this one here, is going to be a lot louder. And then frequency has to do more with pitch. So amplitude has to do with loudness, and frequency has to do with pitch. So how high pitch something is, you know, for those of you that are in chorus, you know, you have like the tenor noises or like the bass noises that are like a lot lower, and then you have like your soprano notes, which are really, really high with a high pitch. So thus these two are going to be related. So now we're going to look at the interactions of sound waves. So we still have to deal with how sound waves are going to reflect off of objects the exact same way as light waves did. So with reflection, you have, you know, your wave coming in this direction, and then it bounces back. And this is how we get an echo. All right. Diffraction is like how I can be like, I don't know, talking really loudly in the hallway and y'all can still hear me in the classroom. So again, the sound wave is just going to come in and they kind of disperse going around that barrier. So we're still dealing with diffraction being a barrier, going around barriers. It doesn't change. Refraction, it can change again. You're still going through two different mediums. So if I'm yelling in one room and then, I don't know, I go into water and start playing music really loudly. I don't know, these examples are terrible, but you see what I'm trying to say. Refraction, you're still going through two different mediums. So like I said, the reflected sound is going to be your echo. That's kind of all you really need to know from here. Sonar actually uses echoes to like determine how deep something is or what's going on underwater. You know, they just go beep, 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 and then it bounces down, and then it goes, oh, beep, 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 because it bounces right back up because it, you know, it reflects the sound. This is also what bats use to be able to find their next meal because, again, they're blind. So they just kind of beep, beep down one way, and they're like, oh, I found something, and then like beep, beeps back up. Yeah. They're actually starting to find different ways to use sonar to help people who are visually impaired so that they can actually like find things. There's this one guy who actually does use sonar. He clicks his tongue and it helps him determine how far something is. Maybe I'll be able to find that video for you guys. It's super cool. So sonar would be an example of which type of interaction, and that would be reflection, because remember, it's echoing, it's going down one direction, and then it's bouncing right back up the opposite direction. So that's going to be reflecting off of one surface. Radar systems send out sound waves through the air. And so by measuring the length of time between the emitting pulse and hearing the echo, that's just kind of how we use radar. You don't really need to know much about this. We probably won't really ask you about that. Echolocation, same deal. So I was talking about the bats. We're still dealing with what do you call it? Reflection. Because bat sees or hears little insect noise hits bat now knows how far the insect is. I really am going to try to find this video for you guys of that blind man who is like clicking his tongue. It is the coolest thing ever. I'm gonna probably give it to you guys on Thursday. Super cool. Sound waves, we also can use ultrasound. I know you guys have heard of ultrasounds. You know, if you have like a baby brother, baby sister, baby cousin, babies in general, they use those sounds to be able to find the babies. So they use ultrasound. So we can't hear it, but we can kind of like take those sound waves and transform them into like something visual for us so we can actually see the babies. But you don't have to do too much about that. So these are just different ways that we can use sound waves. Again, important, but not really. More ways that we use sound waves. Again, important, but not really. And now we're down here to interference. Constructive interference, deconstructive interference, the exact same thing as we talked about before. We were actually already talking about sound waves before when we were talking about light waves, because they do the exact same thing. Constructive interference, their waves are going to meet up and create a louder wave. So when they produce a larger wave, if you don't already remember this from last unit, then yes, write it down. If you do, then smile because you remember. Congratulations. But if two waves are meeting together, like wave 1, wave 2, they meet together and they create one giant wave, then that's constructive interference. But if we have two waves, so we have wave A, wave B, that come together and that ends up creating like this more straight line here, which is like a smaller wave or just no wave at all, then that's going to be destructive. Quiz. So, noise canceling headphones. I told you we're not very creative here. There's always going to be noise canceling headphones. Noise canceling headphones are based off a sound wave technology where the waves are emitted that cancel out the surrounding area. So that is going to be destructive because it is canceling something out, right? If it's canceling something out, it's destructive. If it's building another wave, I don't know what I was trying to draw, but that's going to be constructive. Again, that's just another example here. Constructive interference, they're going to build on each other, and we can see that here. They're building on each other. Deconstructive means that one is going up, one is going down, and so it ends up making a smaller wave here. And then we have constructive again, one's going up, so it's both of them going up. And that is pretty much it for the for this Nearpod. If you have any questions, I'll be back tomorrow to answer any of them. So please write down your questions. I'll be here obviously on, what is it, Wednesday? I'll be back Wednesday to answer any questions that you guys have. Just write down your questions. I'll be